In our previous video lecture, we talked about exponential growth models. In this video lecture, we're going to talk about exponential decay models, very similar. Our objective, find and evaluate equations of populations that obey the law of uninhibited or continuous decay. So uninhibited or continuous radioactive decay, a lot of this has to do with radioactivity and chemicals that decay at a certain rate. And so we've been looking at uninhibited radioactive decay, and we saw this function before, this exponential function. The amount at time t is equal to the initial amount times e raised to the rate times the time. The difference between growth and decay is in the rate. In growth, the rate is always positive because things are growing. In decay, the rate is negative because things are decaying, going down. So A of t, the amount at time t, A sub 0, the initial amount, K is the decay rate. It's the percent written as a decimal. Again, note that with decay, the K is less than 0, and T again is the time. So exactly the same thing, the only change is right here. Growth, the K is positive. Decay, the K is negative. So let's take a look at two examples. In our first example, example 1, iodine 131 is a radioactive material that decays according to the function A of t, the amount at time t, is equal to the initial amount times e to the negative 0.085, to the negative 0.087 t, where A sub 0 is the initial amount present, that's the amount present when time equals 0, and t is measured in days. We're going to assume the initial sample, which is the initial amount, is 200 grams. Question A, what is the decay rate? Well, the decay rate, we know that this K, all right, this K is the rate. So the decay rate, so we have this. The negative tells us it's decay. Okay, so we don't need to put the negative into our decay rate. It tells us it's decay. We change the 0.087 to its percent. Okay, and we can say the decay rate is 8.7%. Again, we don't put a negative in here. We don't say the decay rate is negative. When we're saying the decay rate, we know it's negative because it's decaying. Just like when we said the growth rate, we didn't put a plus in front. The growth rate is this percent, the decay rate is this percent. The negative tells us it's decaying, so then we just look at the rate. Okay, question B. How much iodine 131 is left after 5 days? Okay, so let's see here. The amount at day 5 is equal to the initial amount, which we're told is 200 grams, times E to the decay rate, which is negative 0.087 times 5. And we can put that into a calculator. Let me get my calculator opened up. I'll shift this over so I can put my calculator in here. I think I'm good. Okay, and let's say 200 times E raised to the negative 0.087 times 5, And it looks like we're going to have 129.5 approximately grams of material. So 129.5 grams will be how much is left after 5 days. Okay, I got a part C on the back side of my paper, so I've rewritten the function that applies to this problem. When will 100 grams of iodine 131 be left? Okay, that's the amount left. Okay, so 100 grams. I might need a bit more space. Oh, maybe not. Let's see here. 100 grams, equals 200 times e to the negative 0.087 times t. We need to solve for t. Let's first divide both sides by 200 to get e, the exponential piece, by itself. Dividing both sides by 200, and I have e to the negative 0.087 times t is equal to a half, which I'll write as 0.5. Now I'm going to rewrite this. We know we can rewrite this as a log. Okay, so we know that it's a base of e, so the natural log of 5 is equal to the exponent, negative 0.087 times t. Okay, now we solve for t by dividing both sides by negative 0.087, and t is equal to, I'll write it out precisely first, and then I'll do the calculator approximation. T is equal to ln of 5 divided by negative 0.087. And if I put that into my calculator, again, I'll shift this over. Let's take a look at that in our calculator. Okay, the natural log of 5 divided by negative 0.087. And I come up with, it looks, whoops, something happened here. What did I make a mistake on? Oh, I see my mistake. Okay, I bet you caught that again. Here, this is 0.5, so this should be 0.5, the natural log of 0.5. So this should be 0.5. I totally goofed that up, and I'm betting at least some of you caught that. Let's try that again. So the natural log of 0.5 divided by negative 0.087. Let's try that again. I can copy this one, and then I'm going to go back in here and insert a 0.5. So insert a decimal. There we go. Now let's calculate, and I came up with 7.967 days. Well, that is approximately 8 days. So the iodine we will have half of the iodine left after approximately 8 days in this case. Another word for that is the half-life. What is the half-life of this? It has an 8-day half-life. Okay, example 2 here. We're going to solve a little bit more complicated of a problem. Example 2. Traces of burned wood along with ancient stone tools in an archaeological dig in Chile were found to contain approximately 1.67% of the original amount of carbon-14. Some of you may be familiar with carbon-14 dating. Carbon-14 is used because it has a known half-life. It's used to do a lot of dating, the amount of carbon-14 in a source. If the half-life of carbon-14 is 5,730 years, approximately when was the tree cut and burned? Okay, well, we know that, let's see here, we know A of T is equal to the initial amount, A sub 0, E to the KT. We need to find K. So half-life, and we know how long it took to get to half. So we know the T for half-life. So you can use any numbers you want as long as the initial amount is double the ending amount, because half-life means it needs to go down by half. So if you want, what most people probably do is they'll put a 1 in for the initial amount, which means you get a half in the final amount. Half-life. Take the initial amount and you have half left. If you want to put a 100 in here and a 50 here, it works. If you want to put 10 here and 5 here, if you want to put 200 here and 100 here, what it's saying to you is you have a half-life. And so what you're going to wind up with is a 1/2 on the left times e to the k, and we know it takes 5,730 years, so the time is 5,730. So let's solve this. Okay, the 1 obviously is not going to affect this, so I'm going to rewrite it with the e on the left side. Why not? 5,730 times k equals a half. And again, half-life is going to wind up with a half on one side of the equation. Okay, let's rewrite this using natural logs. It's a base of e, so natural log has a base of e of 0.5 is equal to 5,730 times k. Divide both sides by 5,730, and I have k is equal to natural log of 0.5 divided by 5,730, and I come up with a k that is approximately, okay, let's get my calculator out. Make sure my paper is somewhat straight. Okay, natural log of 0.5 is in the numerator. The denominator is 5,730. And I have a, whoa, that's quite a decay rate. It's very slow. 10 to the negative 4th. Let's write this in standard notation. This is going to be negative 0.00012097. Okay, so let's see. I think that's going to be it. Let's see what I got here. Move my paper so everybody can see. 21209. And I rounded that to a 7. I rounded the 6 to a 7. We'll do 6.8. We'll go a little bit further. Okay, so what do we know? We know from this that we have a negative k. Remember, the negative says. The negative tells us it's a decay rate. Okay, if we change this to its percent, this is equal to negative times 100, 0.012096.8%. So it's a decay of 0.01%. It's decaying by a very small amount. Carbon-14 takes a long time to decay. Okay, so we have K. That's quite a, we'll use this, that's quite a long decimal here. So, this stuff was found to contain approximately 1.67% of the original amount. Okay, so now we know, again, let's go A of T is equal to the original amount times e to the k, negative 0.000120968 times t. There's my formula, there's my function. All right, we had this much of the original, so let's do this. Let's say the original amount was 100. Okay, what we had left was 1.67. That's one way to do this. We started off with 100, and we have left 1.67. We have 1.67 is 1.67%. If this was 1, we would make this as 0.0167. Your choice. I just chose to use 100 times e to the negative 0.000120968 times t. Okay, now we know we divide both sides by 100, and here is your 0.0167. Okay, so there's your 1.67% written as a decimal, which is right up here. We want this much to be left. And now we know the drill. We have our exponent term by itself. Its base is e, so let's take the natural log of, this is the argument, base e, base e, base e. This is the exponent. The natural log equals an exponent. The log equals an exponent. 1, 2, 0. And we're here. Let's divide both sides by this whole thing. So t is equal to the natural log of 0.0167 divided by negative 0.30 120968. And I've already done this with my calculator. If you put this in your calculator, you'll say it is 33,830 years ago. Okay? If the half-life is this, approximately when was the tree cut and burned? 33,830 years ago. Okay? So there you have it. Look at both exponential, continuous growth and continuous decay. Again, our focus remains with this formula. If our rate is positive, we have growth. If our rate is negative, we have decay.